My name is Erik. Together with the Colchester-based Center of Excellence team, I'm responsible for the design support and also for this design validation of car park ventilation and fire safety systems. And as Erik already said, today I'm going to do an introduction on car park ventilation systems, in which we will primarily focus on the different sort of structures, their requirements, and how we would be able to include and design a car park ventilation system for those structures, with the main focus on the concept of using jet fans. Before we start talking about the actual requirements and how to design the system for car parks, you also need to understand why there is a need for a ventilation system in car parks, or ventilation in general. Doesn't necessarily have to be a mechanical system. In this presentation, I refer mostly to the British building regulations. And that's not because we're a British company, but we've learned that most of the requirements within the building regulations in the UK are actually also applied in other countries, specifically or especially in Europe, as well as in the Middle East. Most of these systems are actually what we call dual NOx systems. So the system requirement is there for day-to-day operation to safeguard a healthy condition in the car park, so reducing mostly carbon monoxide levels, and a system that will deal with smoke in the event of a fire in whatever way it's dealt with. We will initially focus on the day-to-day operation. That's the main purpose of having the system in the car park, but later on in the presentation we will also touch on the requirements for smoke extract or maybe even smoke control in car parks. Now, when we consider the building regulations, it recognizes basically three different structure types: an open-sided car parks, partly open-sided car park, and fully enclosed car parks. And as I said, when we talk about ventilation, we, as engineers, mostly instantly think of fans and probably ductwork or jet fans, but that isn't a necessity depending on the sort of structure we are facing. So if we look at the open-sided car parks, within the building regulations, it provides some fundamentals, and if it meets those requirements, the car park can be considered naturally vented, which means that you don't need any mechanical means. And in most countries, they follow the same approach, mostly referring to a percentage of the floor area available in open vents in walls in the car park. So if we follow what's in the building regulations, it says a minimum equivalent natural vent area of 1/20th of the floor area, from which a minimum of 25% should be available in two opposing walls. Now, I'm an engineer, so I always prefer pictures and images and drawings. So basically what it says is, if you take a car park, a simple structural design with floor area of 2,800 meters squared, then 1/20th of that area is 140 meters squared, and that needs to be available in permanent vents to atmosphere. And it needs to be at least 25% in two opposing walls. So if you would just take this car park and you say, okay, we have only fans in two opposing walls, so we haven't got anything on the east or on the west facade, then you need to have half of the 140 meters square in two opposing walls, so 70 meters square each. However, it might also be divided into 50 meters squared, and then if there's openings on the east and the west facade, then the balance of should be available in those facades. So 50 meters square and then 20 meters square could be an option, and the minimum would be 35 meters square in two opposing walls. So that's the 25% of the 140 meters square. So a car park that has 2,800 meters squared requires 140 meters squared in permanent openings, from which the minimum should be 35 meters squared in two opposing walls. This would require no mechanical ventilation as per the book. Now, thanks to modern technology, we are able to do some simulations on airflows in car parks, because the airflow in car parks is quite often difficult to assess because you've got quite often things like columns and other structural obstructions within the car park. But if we take this open-sided car park, a top view, and if we put some moderate wind pressure on one of the facades, which is the north facade on this drawing, you see a colorful picture which represents velocity. Now, if you look at the legend on the right-hand side, you see that anything that is blue is fairly a low velocity, and if it moves towards the red, it's a high velocity. So on this image, you see some light blue, which means that we do have some velocity. Now, this image on itself is interesting, but what's more interesting is the second image, which is an image showing the actual air change rate. So this actually shows you the air distribution in this car park. Now, you can see that overall we seem to have air movement, except for some areas on the left and the right-hand side. Now, on the left-hand side, there is an obstruction, for instance. You see that's this crossed area in the middle, which is white. And you see that around those areas, we actually have a very low air change rate, even to the level where you could say, well, that's almost an area of stagnant air. And areas of stagnant air is something we want to avoid in car parks because those are the areas in which carbon monoxide will start to build up and could actually build up beyond levels which are considered safe to the public. But overall, the system, depending obviously on the elements, whether it all relies on the sort of wind pressure you've got, high winds, the system will work much more efficient compared to situations where you got low winds or no wind at all. Now, from experience, there are car parks out there which meet the full requirements for natural ventilation, but there's also a good number of car parks that do provide openings to atmosphere, but do not meet the requirements for the fully natural ventilated car parks. Now, that is recognized also in the building regulations, where it says that, okay, if you have a car park that does have openings to the outside, not meeting the 1/20th of the floor area, for instance, meeting the 1/40th of the floor area, then you will require mechanical ventilation, but not to the extent of a fully enclosed car park, which we will touch on in a minute. So these systems will require a mechanical system capable of providing 3 air changes per hour. And the background on this is that the mechanical ventilation system is actually only really designed to support the natural draft in the car park. And the reason that it has a fairly low air change rate, certainly if you compare it to the air change rate, for instance, for smoke clearance, which we will touch on in the next couple of slides, the system is primarily there to support the natural ventilation, make sure that you don't have these areas of stagnant air. And for smoke, it is considered to be naturally ventilated, so that the smoke, that you actually have natural smoke dispersal as a result of natural buoyancy of warm smoke in a car park. But that's a subject we'll talk on separately in this presentation. Now, again, in an image, partly open car park, the same car park, 2,800 meters squared, 1/40th of the floor area equals 70 meters squared. Taking the average height of, say, 3 meters, that would mean that for this system, or for this car park, you will require a mechanical ventilation system capable of providing 7 meters cube per second for day-to-day ventilation maximum. The third one, in terms of structural design, is a fully enclosed car park. Now, as an engineer, I prefer this one. Fully enclosed, so no natural vents to atmosphere, either because it's just a block of car park or it's on the ground. And these car parks require a mechanical ventilation system for day-to-day operation, designed around 6 air changes, and a mechanical extract system to provide at least 10 air changes to provide what we call smoke clearance. But again, we'll talk about smoke a little bit later. Now, traditionally, when we talk about mechanical ventilation systems, we mostly would be considering a ducted system. to distribute the air throughout the car park. Now, the downsides of these systems, as we can already see on the images, is space requirement. And space in car parks is generally an issue, because from a structural perspective, you try to build a car park as low as possible, simply because that saves you a lot of money on things like excavation. But it leaves us very little space for mechanical services, and especially ductwork is a nightmare in car parks, because of this limited space. You often end up with duct design that is not ideal from an efficiency perspective. Now, for the fan engineers listening in, if you look at the upper right image, you'll see an actual flow fan with two rather awkward transition pieces. Now, obviously, you can almost get anything to work, but from those transition pieces, you can already see, well, this is not going to be a very efficient design from an energy perspective. So you would require quite a lot of power on the fan motors to actually push that air through that ductwork to overcome the duct resistance. So apart from the fact that it's difficult to get the space for the ductwork itself, as a result that you get quite awkwardly sized ductwork, which often turns into a lot of resistance, which turns into larger fan motors, which turns into more money to operate the car park, because it will take more energy to move that air through the duct. Now, if we would look at a traditional design, again, fairly straightforward and simple car park, now based on a ducted system. So what I've done here is along the say northwest facade, and on the west facade I've put some supply points in representing the ductwork, and on the south facade and on the west facade partly you see the exhaust points, again representing the ductwork. So if we would do a simulation on this, this would be the airflow pattern. So in comparison to the natural ventilation velocity contours, you can see that we have quite some velocity in the car park thanks to that ductwork. But again, more of interest would be this image, the air distribution contours, which show that this system is designed to meet 6 air changes per hour, and you can see based on the color gradients and the legend on the right hand side that that requirement is met in almost every part in the car park. There's an area of which is slightly less in terms of air change rate on the upper right hand, but that generally would not be a concern, as you can see, because the overall car park is properly vented, meeting the requirements. Now, that's great. But this is a car park you would generally not see, because it doesn't have any enclosures within the structure itself, apart from the columns you see. So I've altered that design a bit towards something which is more realistic. A car park that includes things like, okay, probably a stairwell. When it's part of a commercial development, it's probably in lobbies where escalators come down, so causing obstructions in the car park itself. Now, if we would keep that same ductwork in the car park with those structural obstruction in, and we would run a simulation again, you will see from the velocity contours that, yeah, we have still have velocity in areas of the car park, but there is an area of concern which is right in the middle, underneath that first structure, where you can see that velocity seems to be relatively low. And we can confirm that again by looking at the air distribution images of that same car park. You see that over half the car park, or let's say a quarter of the car park, is not meeting the requirements. So it doesn't meet that 6 air changes per hour. And again, that could be areas where air will become stagnant, and again, where CO could build up beyond acceptable levels. So the workaround on that would be to alter your ductwork design, probably with some further extensions down into those areas of concern. But again, the downside is that you're extending your ductwork, you're increasing resistance, and obviously increasing the size of the main extract fans, which is possible, but it's going to cost more money, and certainly to operate that system the operational cost will also drastically increase because of the power consumption of the main extract fans. Now, we could obviously say, okay, well, let's forget about the ductwork and let's put a single point of extract in this car park, which is on this image in the lower left corner. And let's utilize the entrance ramp as our fresh air supply, which, if it's a single level car park, is possible because mostly those entrances are open, or you could make them at least partly open by using a open sort of roller shutter, and get the fresh air in naturally instead of mechanically, because that's our first saving already. If we can utilize the entrance ramp, we don't need mechanical supply fans, which obviously is a cost saving and certainly an operational cost saving on the longer run. So you could do a design like this, say, okay, well, let's put a single point of extract in. Yes, let's utilize that natural fresh air supplied through the entrance ramp, and design around that. It's a possibility, but it will end up in a result which is on the screen here. So again, based on velocity, you see a very a considerable velocity coming from the entrance ramp, but the downside, it's moving only in a sort of corridor straight into the extract point. So if you would drive into the car park towards the extract point, you would be in an area which is properly vented, but the remaining part of the car park is not receiving too much velocity or ventilation. And again, that can be substantiated by doing a simulation based on air distribution. And you can see that over half the car park is a real concern, because this turns up to areas where the velocity is, well, zero or at least close to zero. Again, turning into areas of stagnant air. So the solution based only on the supply point and the extract point is not going to be very well, and certainly not going to meet the requirements to have an even air distribution equal to 6 air changes. So if we want to avoid the use of ductwork because of all the nuisance but related to the high pressure losses turning into high motor powers required, we could consider another concept, a concept which was introduced in the mid-90s, around 1995, called the jet fan technology. And basically, the jet fan technology is a spin-off, or jet fan technology for car parks is a spin-off of the jet fan systems used in road tunnels, but basically adjusted to the needs in car parks. And again, the main need in a car park is the issue around space. So the concept of the units is exactly the same as a jet fan in a road tunnel, but where in a road tunnel we probably could work with jet fans up to 1.25 meters in diameter. In car parks, you can generally only accommodate something like 350, maybe 400 mil maximum, and sometimes even less than that. And basically what a jet fan is, it's an axial flow fan with 2 sinuses attached to it to obviously provide appropriate attenuation so that the noise levels will not exceed the maximum acceptable levels in the car park, and B, to make sure that you've got a laminar airflow coming out of the jet fan, so that you do away with the swirl which comes from an axial flow fan, so that you get a proper flow of air coming from that jet fan. Now, over the years, there have been some further developments. So apart from having axial flow fans, jet fans, we also see what we call induction fans, which in terms of system design and performance is the same. The only difference is that those units are based on centrifugal fans. So you have the intake at the bottom and then 90-degree angle and the air goes out. The unit is a different concept. The upside is that generally the units are smaller in depth. So if you have a very shallow car park, you can quite often get away with induction fans rather than axial flow fans. But the concept and the way you design the system is actually exactly the same. So it's all based on what we call positive forward thrust. And we'll look into that in a little bit more detail in the next couple of slides. On the screen, you see a open space, or it's enclosed space, but it's a space of 100 meters by 50 meters, with on either side the blue rectangles, an opening to outside. So we've got an opening on the left-hand side, and we've got an opening on the right-hand side, and we've got a jet fan mounted in the middle. Now, if we take a top view and a top view on velocity contours, you will see the jet fan, which is not running. So you'll see little to no air movement in this car park, which is going to change when we switch on the jet fan, and then you'll suddenly see that something changes in terms of the velocity contours in the car park. What's important to understand is how this concept of the jet fan actually works, because I've had a lot of discussions in the past where people said, well, okay, you have 6 air changes on the extract point. So let's take the jet fans and let's add up the nominal airflow of the each individual jet fan to make sure that that is in line with the 6 air changes on the extract point. But that's not the way this jet fan system works, because what the jet fan actually does is it generates a high velocity on the outlet. And by that high velocity on the outlet, you create areas of positive and negative pressure. And especially those areas of negative pressure are interesting because the negative pressure starts on, or you have on the sides, on both sides of that jet coming out of the jet fan. So the orange arrows on the screen. And what's interesting is that by only running that single jet fan with probably, say, a nominal airflow of, say, 5,000 meters cubed per hour, you're not only moving the 5,000 meters cubed per hour, which go through the fan, but you also move the surrounding air because of these areas of positive and negative pressure. And it's quite impressive because it depends a bit on the structure in which the jet fan is mounted. So it depends a bit on the structural obstructions around the jet fan, but in that open space, it could be what we call an induction factor of up to 4 or 5 even. And basically that says that, okay, if we have an induction factor of 4, the equivalent airflow of the jet fan in the car park is the nominal airflow of that one jet fan, say 5,000 meters cubed per hour. And when it's an induction factor of 4, the actual equivalent airflow moved in the car park is 4 times the nominal airflow of the jet fan. So if it's 5,000 meters cubed per hour and you've got an induction factor of 4, the actual equivalent air movement in the car park is not 5,000, but 20,000 meters cubed per hour. And that's a great benefit because that will actually provide you with an even airflow throughout the car park only by using a number of these jet fans around the car park. What is important, however, is that when you consider a car park with a certain extract flow rate, you always have to make sure that there is a balance between the two. So you have to bear in mind that, okay, my induction factor could be on the project, say, again, 4. That will mean that we have to be very careful that there remains a balance between the air propelled forward by the jet fans relative to the extract point. Because if you don't, what will happen is that you'll probably will be faced with what we call backflow. So you're pushing a lot of air towards the extract point, but if the extract point can't cope with the air moved forward to that point, then that air will come back into the car park, which will actually reduce the efficiency of the system. So always have to be cautious with especially the number of jet fans in a car park to make sure that there's always a good balance between the two in order to make them the best and the most efficient system design. Now, it's also interesting, and I just included that picture or those images as reference. So if we take that same space and we put in a number of jet fans, so we've just seen the results from one, but let's put some, what is it, 8 11 jet fans in this car park to see what will happen if we run those fans in this space together. Oh. Again, on velocity, you will see the jet fans, the high velocity at the core of the jet fan, and you see a lot of air movement and velocity going around in the car park. Again, nice image, but what's more interesting is this image, because this actually shows you that with a number of jet fans, and if you have this ideal situation where you've got an opening on the one side and another opening on the other side, that with only jet fans, you could actually generate air movement in the car park to an extent that you could actually meet, for instance, that requirement which we saw in the second slide talking about the partially open-sided car parks, that you could actually design a system that doesn't require mechanical extract fans to provide that free air changes, but you could use only jet fans to generate that. Now, in the past, it was often quite hard to understand or to substantiate, but thanks to the modeling technology, because all the images you see on the screen are actual flow analysis we did. So with this, you can substantiate that in that specific car park, we could provide the client with a system in compliance with the free air changes, but only based on the use of jet fans. Now, obviously, when the structure gets more complicated or the opening sizes will be substantially reduced, then it will become more of a challenge, but it is doable. So you could do a design providing an air change rate based on jet fans only, thanks to that effect, what we call induction. Now, if you go back to that same sample we looked at before with the single point of extract and the structural enclosures within the car park, we saw the results when we run the system. We have we've got a fairly good airflow at the top straight into the extract point, but in the majority of the car park, the area is not very well distributed, considerable areas of stagnant air. We could consider to put jet fans in to deal with those areas of stagnant air. Now, as a reference, compared to the images around ductwork, I've included a small image from a project we've done some years ago, where you can see the jet fans. They're sitting at high level in the car park. They're not taking up too much space, and they can be positioned basically anywhere where we want those jet fans to be positioned based on the airflow in the car park or the lack of airflow in the car park. So on the layout, you see some highlighted areas of jet fans. So what is it, 4 or 5 in total? Specifically in the area where we saw that the airflow would be low, or even areas of stagnant air. And if we do the same simulation with the same amount of extract, and again, the entrance ramp as our fresh air supply point, and the jet fans as per the drawing, we see that we certainly increase the velocity in that area of concern. And just as a reference, I've put the two images together. So on the left-hand side, you see the results without the jet fans, and on the right-hand side, you see the results with the jet fans. So by only including those 5 jet fans, you can see that the air distribution in the car park has considerably improved, and is now meeting that requirement of the 6 air changes as per the building codes. Now, that's all related to day-to-day ventilation mode. And as said on the first slide, I believe, mostly the car park ventilation systems are what we call a dual NOx system. So they're primarily there to provide day-to-day ventilation to reduce carbon monoxide levels, but also there is obviously a potential risk of fire in the car park. And since these spaces are quite confined, that could be an issue in terms of smoke. Again, as per the UK building regulations, the car park ventilation system is also to be designed to deal with smoke in the event of a fire. and that is defined as being a mechanical extract system to provide at least 10 air changes to provide what they call speedier smoke clearance during and after the fire is being extinguished. And it's important to understand, because this is where we often have a lot of discussions with customers. A 10 air changes system is basically just a ventilation system that provides what we call speedier smoke clearance. And speedier means that, okay, benchmarked against what? In this case, it's benchmarked against the same rate of smoke clearance if there was no mechanical ventilation system in the car park. So this is really only to provide smoke clearance. So to have a system in place that over time will clear the smoke from the car park. But it's important to stress that the time window in which the smoke is to be cleared is not defined. So it's purely a system, basically as the 6 air change system for CO mode. It's a system to clear the smoke after the fire has been extinguished. So not providing any tenable conditions for the public in terms of an extended evacuation period or improved conditions for firefighters in a car park. This is just considered to be a ventilation system to clear smoke. And just to give you an understanding how the system works, I've put together a small animation on a small car park where we have an extract point on the left-hand side, which is sized to meet the 10 air changes requirement in the car park. We've got replacement air coming through the entrance ramp into the car park. We've got a single jet fan here that generally operates in normal day-to-day operation to provide that dilution and air distribution. And we've got some bluish block here, which is the seat of the fire. And if we run this simulation, what you will see is fire starting, you'll see smoke building up in the car park. And at the peak of the fire, which is generally around 20 minutes after fire start, you will see that this car park is fully smoke locked. So there's little to no visibility in that car park. And only after the fire has been extinguished, you will see that the smoke density will start to reduce, which is the effect of the 10 air changes extracting from that car park. Now, what's important to understand is again that 10 air changes is relative to the volume. Is relative to the volume of the car park. So, but the one thing which remains the same is the car fire itself, because that's going to be the same parameters as if it's in a 1,000 meter square car park. It's the same parameters as if it was in a 20,000 meter square car park, but the air quantity extracting from the car park is obviously considerably higher in a 20,000 meter square car park. So reason for putting the emphasis on that is that you can't expect any conditions in the car park. So again, it's solely there to at that point start to extract smoke from the car park, so that at a point you'll have sufficient visibility, for instance, for the firefighters to do their structural survey and things like that. So it's important to understand that 10 air changes is really only a ventilation system. However, when the jet fan system was first introduced, it became apparent that using positive forward thrust of jet fans could actually be utilized to start controlling air flows, but potentially also smoke flows, which would mean that potentially you could do a system that could in fact improve conditions in the car park throughout the development of a fire. But a lot of that was quite unknown and also not in the building regulations. So I think it was 2006 when the first edition of the Code of Practice BS 7346 Part 7 was introduced. And the reason to include this in the presentation is because we have seen that in most countries, the BS 7346 Part 7 is quite often also referred to in specifications for car park projects to outline requirements for in the event there's a fire in the car park. And it's an interesting document because it comprises 3 sections: Section 9, Section 10, and 11, and a Section 11. Now, Section 9 is a section that outlines the requirements fully as per the building regulations. So basically outlining that the system is there to vent the smoke from the car park, but it doesn't say anything about the conditions in the car park throughout the development of the fire. So it's only focused on having a system that clears the smoke after the fire has been extinguished. Section 10, however, is a system that is designed to assist firefighting access. Now, in the past, this was often referred to as smoke control, and often smoke control was associated with safety to the public, but that's not really what it is, because travel distances in terms of in buildings in general, but certainly in car parks, are generally not more than 30 to 60 meters. So any point within the car park, from any point within the car park, you should be able to find the nearest fire exit somewhere between the 30 and 60 meters away from you. So, and if you look at how a fire develops in a car park, there's no reason why people should not be able to find their way out from the car park in the initial stages of a fire. So even though it's an engineered solution, a Section 10 system, it's not so much to allow people to evacuate from the car park. It is to assist firefighting access, making it more likely that the fire service will do an intervention from the inside. Because in most fire service protocols, if there's, say, no sprinkler system or a engineered smoke control system in the car park, then it's a question mark whether they will actually do an intervention from the inside, depending a bit on surrounding buildings, but that leads so far for this presentation. So the Section 10 is a more engineered solution where we basically provide what we call tenable conditions for firefighters. And a Section 11, I've included it because it's included in the BSF 446, but well, in my working career, since the launch of this document, I've never really seen a Section 11 design, which is an impulse ventilation system to protect means of escape, which is basically focused on extending the evacuation period, which I think should not be something you should look at, because again, the building needs to meet the building regulations in terms of fire safety. And if the building regulations outline a minimum number of fire exits, then that's something you would design to as a structural engineer. And I find it particularly scary if you would do a design only relying on one escape route and then protected by mechanical means. So just so that you're aware that Section 11 is included in this document, but I would not put too much emphasis on it because, as I said, over the years I'm in the industry, I've never really seen a Section 11 design. So just to go through that Section 10, which is an engineered solution, so not based on the 10 air changes, just to show you what the design requirements are, and this is a snippet taken from that code of practice. On the screen on the right hand side, you see the seat of the fire, which is this little gray circle. What the code of practice says is that a region around that seat of the fire, which is 10 meters, that's a region in which visibility may be 0. So a lot of smoke and no visibility. But you see an area which is referred to as 4, which is what we call the approach path of the fire service. So fire service comes in from, say, a protected stairwell into that car park. And then what the system needs to maintain is a relatively smoke-clear smoke path for them to approach that seat of the fire, in which the visibility needs to be at least 10 meters. Now, again, I prefer drawings and animations. So to just show you what that system should do, I've included this animation. As you can see, a larger floor area car park than the one we looked at for smoke clearance. You see an increased number of jet vents, extract points on the left-hand side, and you can see the seat of the fire, which is the blue block in the middle. And when we run this simulation, what you will see is the same effect. You see smoke starting to build up. It spreads throughout the whole car park. And then at a certain point, we'll start the ventilation system or the jet fans, often with a delay of around 3 to 5 minutes. And what you will see now is that there is an interaction between the jet fans and the extract point, which leads to a situation where the right-hand side of the car park, so from the entrance ramp, which is generally the preferred approach path of the fire service because it's more convenient for them to go in with their hoses. You can see that that area on the right-hand side is, well, at least what we can call considerably clear smoke. So the visibility in that area is more than 10 meters, which means that for them it's much easier to go into the car park and locate the seat of the fire. But probably more important is that they will not lose their bearings within the car park, so they will not be trapped by smoke if for whatever reason the situation gets out of hand. So they always have a free approach path towards the seat of the fire, but probably more important, they also have a free path back to the point of entry into the car park. So that's what we call the system design in compliance with Section 10, providing tenable conditions for the fire service. Now, it's important to stress that this is a full engineered solution, which means that we step away from the 10 air changes. That's not relevant for these designs. What's relevant is expected fire size, and as a result of that, the buoyancy of the smoke, the temperature within the smoke, and that all translates into critical velocity. So in general, the extract flow rates on a Section 10 system are excessively more than the 10 air changes you would see with the smoke clearance system. And also needs to be understood that a engineered solution, so a Section 10 solution, can only be designed for a car park that's big enough. So car parks anywhere below, say, 5,000 meters square in floor area, for those car parks, it's impossible to design a smoke control system or a Section 10 compliance system. And if it was already possible, then it would not be very practical because the plant sizes for the main extract fans would probably take up half the car park space. So not very practical. So again, one thing is that's important to realize is that the Section 10 design can only be done in a car park which is big enough, so anything over 5,000 meters squared, and it's not based on a fixed air change rate. It's based on a full engineered solution on which the extract flow rates are generally excessively more than a traditional 10 air change system. With that, there's a few other things I want to raise in relation to that Section 10. It's important to understand that it's not mandatory in most countries. So reference can be made to it, but it's not referred to in any of the building codes and standards, except, I believe, in the UAE, in the Middle East. Again, it's a fully engineered design, not based on fixed airflow rates or air change rates. Minimum floor area between 4,000 and 5,000 meters squared. It does require a fully addressable fire alarm system because we need to know where the fire is located in the car park to initiate the appropriate ventilation strategy. And it also requires consultation with the local fire authorities in an early design stage. And that's because mostly the fire service will have a number of strategies for a specific building. So it might be that the preferred entrance into the car park for them would be the entrance ramp. But if for whatever reason that's not usable or they can't reach it, they will always have a second point of entry into the building. And with a Section 10 system, it always have to provide the tenable condition for firefighters based on the point of entry. So generally, the minimum number of point of entry that they have into the car park is 2. So when you do a Section 10 design, the Section 10 design should always be based on 2 scenarios, which could mean that you would have to have a reversible system because the one exit is on the the one entrance is on the one side, and the other entrance they might use is on the other side. Then obviously you need to be able to reverse the flows in the car park. So it's a fairly complicated design, and it requires full validation through extensive CFD analysis. And especially that part is critical because you need to be able to prove that you can actually maintain those conditions, and it has to be done through CFD analysis, which will take a considerable amount of time to run through, but we'll touch on CFD analysis briefly a little bit later at the end of this presentation. A bit on controls. Generally, this would be sort of the setup. So you've got a central control panel. You've got main extract and maybe also supply fence if there's a need for mechanical supply. Mostly nowadays operated through frequency inverters, which is a bit associated to the incoming controls, which I'll touch on in a minute around CO detection. You obviously need smoke detection. When it's a Section 10 compliant system, then you need an addressable system because you need to understand where the fire is located. But also for a smoke clearance system, you often need to have it in place to trigger the system into smoke clearance mode. And on the left-hand side, you see the jet fence. Just focus on the CO detection. As I said, the requirements in the building regulations are set at 6 air changes per hour. Now, this is a bit of a dodgy one because if you would not include a CO monitoring system in the car park, then basically the document says that the system needs to run at 6 air changes 24/7. Now, apart from the fact that it is a nuisance and it's also not very, let's say I mean, you're not considering the conservation of power. Let's put it that way. You don't need full ventilation all the time. I mean, take a residential development. Typically, you have some peak traffic in the morning and peak traffic in the afternoon, and in the hours between, you've got very little traffic. So no production of CO, which means that you don't need the full 6 air changes per hour. Now, fortunately, the building regulations do allow us to reduce the airflow to a lower ventilation rate, but that does mean that you have to have CO monitoring in the car park that will monitor the level of carbon monoxide in the car park and adjust the ventilation rate to that. So if there's no carbon monoxide, then the system might run at a very low speed or maybe even only in standby. And when it increases, the whole system will ramp up in different steps to the full capacity of 6 air changes. So the car park ventilation system will still be designed to meet the maximum of 6 air changes, but it's not necessarily said that the system will run at 6 air changes if you have a gas monitoring system in or as part of that overall control package. Now, I've had a lot of debate, certainly in the past, because CO monitoring is not specifically referred to in that building regulations. And obviously it is an additional investment in the overall system. No, when I did my calculations a couple of years ago, I based it on the energy price level at that time. But with the increasing price levels nowadays, I think the payback time of a CO monitoring system probably would be less than a couple of months. So apart from the fact that as engineers, we are obliged to follow an approach where we also consider the conservation of power, it is actually something which will make the car park safer in terms of the conditions of CO in the car park, but certainly will also save a lot of money on the operational costs. So even though it's not specifically referred to in the building regulations, I always highly recommend the inclusion of a CO monitoring system because it gives you more flexibility and will certainly result in lower energy costs or running costs for the system. Just briefly, what is included? As I said, it's not specifically referred to, but indirectly it is. It says that you have to maintain conditions in the car park that would not exceed 30 parts per million of carbon monoxide over an average over an 8-hour period. So you need to read it closely, because that might allow you to actually go up to 60 or 70 ppms, as long as the average over 8-hour period is not exceeding more than 30 ppms. However, there's a maximum threshold also referred to, which says that the peak concentration should not exceed 90 parts per million. So if it's 70 only for an hour, then you might, and the remaining time it will be 10 or 20 ppms, then the system is still compliant as long as it not exceeds the 90 parts per million over a 15-minute period. But those logics are generally all included in the CO control panel, so that will actually do the measurements for you. Now, then lastly, something I briefly wanted to touch on, because it has become very popular to do CFD analysis on car parks. Now, in the presentation itself, you've seen that I've included a lot of these simulations, which is actually a very good engineering tool, because it does allow you to simulate accurately simulate the airflows in the car park. I must say, however, that there is an increase in the requirements for CFD analysis, but the downside is also that quite often people are not really trained to understand the CFD analysis. It is a subject on its own, so you could have a couple of hours presentation on CFD analysis. Just briefly want to touch on the main things around CFD analysis. Now, this is a service which we provide as a Center of Excellence team in Colchester. And basically what CFD analysis is it's basically solving equations, Navier-Stokes equations, with which we can generate the images I showed you on the screen in terms of velocity profiles. You could do air quality simulations, smoke spread, smoke density, visibility, and temperature distribution. And the way we do it is that we take a structural design. That structural design is then divided into what we call cells, and in each cell a number of these Navier-Stokes equations are solved, which will give us the data to generate those images. Now, probably the most important thing I want to put the emphasis on this part is that the quantity of cells is the important bit in doing CFD simulations. Now, I've seen people out there that seem to be capable of doing simulations in maybe, say, half an hour, which probably is doable, but that means that you will probably use bigger cells, so a lower quantity of cells in the domain. Now, that is a possibility. The only downside is the accuracy of the actual flow analysis is dramatically reduced. So the bigger the cells get, the quicker your calculation goes. In terms of the images, it seems the same. So that's the issue we quite often face when we have discussions with customers, is that the images, you can't really see it from the images. So it's data you actually have to get with the CFD simulation to assess whether it is a simulation which you could use as, say, a provisional validation of a design. But if you want to do, for instance, a simulation on that section 10 I showed you, so it's a smoke control system, then the accuracy of the simulation is very important, which means that the cell sizes will have to become smaller to make it accurate. But again, the downside is that that will take considerably longer to calculate. And just to give you a reference, I mean, there are projects out there on which only one smoke simulation with us took a couple of days to complete, even though we've got state-of-the-art computer technology. But it's to come to those accurate images to validate a section 10 design, for instance, will take a considerable amount of time, because it has to be very accurate. Now, just some sample images from full CFD analysis, and we have seen those before. You've got streamlines or velocity contours, but you could also do what we call velocity factors, which will give us an insight on how that air actually behaves, whether we've got recirculation, for instance. But also it will result in simulations on, for instance, in this case, smoke clearance rate. So starting off with on the left-hand side with a fully smoke-locked car park, and on the right-hand side the results over a certain time to show the actual rate of smoke clearance. Now again, if it's smoke clearance system, which the majority of car parks actually are, because that section 10 is not mandatory in most countries, the image cannot be really used to accept or reject the system. It will give you an indication on what you can expect of the 10 air changes in that specific car park in terms of smoke clearance rate. Now, whether that shows that smoke is cleared after 5 minutes or after an hour, that's not really relevant. So that's not something for which authorities can say, well, it's accepted or rejected. It's purely an indication on what the 10 air changes, probably together with the jet vents, will result into in that specific car park.